Do you remember this is what we did last time we talked? We were talking about transformations, and primarily everything we were doing was either moving things left and right or moving things up and down. I think we talked about a lot with your class when it was like inside of like the absolute value or inside the parentheses or I guess inside the parentheses again, that's when you're moving things left and right. When it's outside of the parentheses, when it's outside of brackets, when it's outside of anything, if it's not under the square root, if there's no parentheses, that's when you move things up and down. So I'm gonna have you do some basic transformations on the quiz tomorrow. And what we're about to do now is we're gonna skip and do some on the graphing calculator so we can expect what to see and then see it. Yeah, William. The quiz is no graphing calculator tomorrow, great guess. There's some more BFF stuff on it too, so we'll break down what that looks like. But everything we do today is only gonna help you prepare for the quiz. It's not adding new material that will be on the quiz. So I actually want to skip number 2 for right now, and I want to jump to number 3. It says sketch on a calculator. So we're going to graph these on your calculator to get your calculator out. And I would guess, except for letter E, that you can make the assumption about what's going to happen in each graph, okay? So get your graphing calculator up. We're going to graph, and then it says find the domain and the range. So we're going to do that together. One thing I want you to make sure that your plot one is not highlighted, make sure it's just the y equals, and then I'm just gonna be in a standard window, -10, +10 in each direction. Okay, so when I look at that first one on my first problem number 3, sketch on the calculator, before you even sketch it, what do you think is gonna happen? What do you think that -5 does to my graph?
Move it down, right?
Move it down 5. See how there's no parentheses? So it's not inside the x squared, it's just that -5 by itself. So we're gonna go prove that. We're gonna go do x squared -5, and it should move my parabola down 5 units. Perfect. And I don't care about anything. I don't care about zeros. I only care about domain and range. If it makes you happy, give yourself a little sketch on your paper to remind yourself that it physically did move down 5 units. What's my domain here? Oh, sorry, Ian.
I'm still on the scatter plot.
Great, so go back to your y equals.
Yep.
And then scroll up so that your mouse is on plot 1
Yeah.
and press enter. That turns it off, right? Then put it in. Yeah, that's great. So let's go to zoom. And go to 6, which is the standard. Yeah, there you go. And you're gonna want to do the same thing, go to zoom. And go to 6, which is Z standard. So when in doubt, I just always go back to Z standard because it should give us most things. Everybody's calculator looks good. It looks like we went down 5 units. What's my domain of this new picture of this new graph? All reals, good. Negative infinity, positive infinity. What about my range here?
-5.
Good. Instead of being 0 to infinity, it's going to be -5 to infinity. Bracket or parentheses with that -5?
Right.
Bracket. Very good. Okay, this next one, it says ln, it doesn't say in. I feel like, did we talk about that a little bit as a class?
Yeah.
That one says ln. The ln button is on the left side of your calculator. It's right below the log button. So go to your y equals and we're gonna press that ln. It looks like the x plus 6 is all in parentheses. So when we go to that y equals and we press ln, keep it, it's already should have given you parentheses, to just type x plus 6 and then close your parentheses. All right, your zoom standard, your normal window should be fine. So we're gonna go graph it. We should know that natural log graphs do kind of look like that. What we might not remember is that natural logs have that vertical asymptote at, normally it's at 0. Normally we have a vertical asymptote here, but since we went +6, we moved everything where? What is that +6 do to my graph? Left. It moves it left 6. And we saw that in the graphing calculator. We also know that we're moving left or right because it's inside the parentheses, but it's opposite of what you think it should be. So since it's a plus, it's going to be to the left. So instead of my vertical asymptote being there at 0, now it's moving over to 6, and my ln graph looks something like that.
I'm just cuts off.
So yours just cuts off because it implies that's the asymptote. So right about, well, I don't know, I'm gonna reach it, like I'm gonna touch it, but like right, like it just has like a tiny curve down, doesn't it? That just implies the asymptote. So that you would see it right at -6 where it comes down. Yep, all of ours look like that. What's my domain for this? What's my smallest x?
-6.
-6. Do I bracket or parentheses that? Parentheses, very good, Ian. We parentheses because there's no real point there. That's where my asymptote is. What about my range? Good, it's all my all real numbers, -infinity to +infinity. All numbers work as my range. And we're gonna do something today that I think is gonna help us kind of organize some of those thoughts, okay? Let's do the next one. The next one is a reciprocal function, 1/x + 3. What do you think is gonna happen to this graph? So what does this +3 do? Up 3. Good, so we're gonna probably move our little C curves up 3 units. So we'll go put that in the calculator. 1 divided by x. And then +3. You don't need any parentheses on this because the +3 is like separate from that fraction. If you wanted to show that that x + 3 was all in the denominator, you would need to wrap that up in parentheses, but we don't have to do that. We go ahead and graph this and it looks just like our reciprocal function. Everything's just up 3 units. So my vertical asymptote is still at 0, 0, but my horizontal asymptote now is at 3, and my C curves just kind of hug those asymptotes. Now my reciprocal's domain and range, remember that we've got asymptotes here. So it's not gonna be all real numbers for either of them. It's gonna be literally everything except for one number. So what's my vertical asymptote that's not part of my domain? What's my vertical asymptote that will not be part of my domain? 0. So we're gonna go from -infinity to 0, and then we're gonna go from 0 to +infinity. All reciprocal domains and range look like this. They will always have one number that's just not included because that's your vertical or your horizontal asymptote.
So why was it 0?
And 0 is the x, and we don't have any points at 0 on my x. Now for my range, now we're looking at my y. So now the only thing that doesn't count now is my horizontal asymptote. So what doesn't count now? 3. So -infinity to 3. 3 to infinity. Okay, we feel all right about that? All right, my next graph is an absolute value graph. What is that -4 gonna do to my graph? To the right 4. We're gonna go to the right 4 units. Do you remember how to get absolute value marks in your calculator? Remember we go to math. And then we scroll over one to that NUM. And then that first option, ABS, is your absolute value. So when I press enter, it makes little absolute values in my calculator. Some of your calculators might still physically have it written ABS, and that's okay. Just pretend those are absolute value signs. So absolute value, x -4. That -4 has to stay in that absolute value. So make sure it stays in there. And then we'll press graph. Perfect, and it moved our little V shape over 4 units. Okay, what's my domain for this? All reals, -infinity, +infinity. What's my range here?
0 is big.
0 infinity, bracket or parentheses with the 0? Bracket, very good. All right, the last one's a weird one because we haven't, bless you, we haven't graphed any greatest common integer or greatest integer, and we haven't done any multiplying or dividing by the x on the inside. So let's go look at what that is going to be. When I go to my y equals, clear it all out. And the greatest integer is actually where you found absolute value. So we're gonna go back to math. We're gonna scroll over to NUM. And if you look down at number 5, see how it says INT? That was the equation for greatest integer, was INT x is like our basic, like that's our BFF equation for like the greatest integer. So I'm gonna click number 5. And it should just pop that little int in my y equals, and now I do x divided by 2. Okay, I'm not sure what to expect because we haven't really done or seen any of these where we're multiplying or dividing x by 2. So let's go press graph. Okay. Does anybody's look like mine where it has kind of like the vertical lines drawn in? Does anyone's not have the vertical lines drawn in? That is a more correct graphing calculator if they don't have the vertical lines. I think the way this calculator works, it's like a computer program, so it just keeps connecting the lines. So we should not have these like vertical lines right here. So if your calculator has them, just pretend like they don't exist, okay? Now let's kind of zoom in. It looks like my stair step goes from 0 and it goes all the way over until I hit 2 or nearly 2. So normally in our greatest integer function, I didn't mean to throw that. I'll just kind of sketch it on the board. Normally in our greatest integer, the closed circle goes at 0, 0, and then I just go over 1 unit, and then I have an open circle. Then I pop up to 1, and then I go closed circle, open circle at 2. And then we keep going all the way. What this is telling us is that this time, instead of going just over 1, now we're going all the way over to 2. So we're still having our closed circles here, but we're gonna go all the way over to 2, and that's where our open circle is. So what happened is that we stretched this graph horizontally by a factor of 2. Now, again, we will deal way more with that later, so I don't really need you to know that, but I want you to see what happened here. That doesn't affect a lot of things, but when I do make my sketch, I do want to be careful with it. I know I took off some petty points on some of our quizzes and tests or quizzes because we had overlap. Whenever you do greatest integer, make sure that they're not like overlapping on top of each other. See how I've got space here and here? That wouldn't be a function. And this is a BFF, which is a basic family of functions. So we can't have that. So when you draw these, make sure that you draw it so they have no overlap on top and bottom. Open, close, open, close, open. That's what it looks like. Now, my domain here, though, it's still hitting all of my numbers, right? So my domain for greatest integer is still, and it always is, negative infinity to positive infinity. If you remember when we talked about greatest integers as a class, the range is funny, and I would never ask you to do a lot with this graph just because it's funny like this. Notice that there's no points in between like these stair steps, which means that the only y's that I'm using are the integers. I don't know if you remember me doing this, but I showed you like this fancy Z symbol. That fancy Z represents the set of integers. Just like this fancy R symbol symbolizes, do you guys know what that R symbolizes? All reals. This Z symbolizes all integers. If you don't like that Z or you can't remember it, you can always write like this brace and then dot, 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 -3, -2, -1, 0, 1, 2, 3. Basically, it just gives a couple examples and it's like, it's just gonna go on and on in both directions forever. Again, this is a very specialized skill. I wouldn't ask you this, like domain and range, but since we're talking about it, we'll talk about it. That being said, it didn't change even though that the graph was not the basic family function, even though we stretched it a little bit, it's still the same domain and the same range. Nothing shifted there. Okay, how are we doing with domain, range, shifting graphs? We feeling okay with that? Okay, I want you to go backwards. We're gonna go back to number 2. That's us kind of classifying our BFF. So every question I'm gonna ask you, our answers are going to be some of the BFF graphs, okay? Again, I don't think this is going to be new information, but it might just help you kind of put the BFFs in little like groups to help you understand and remember some things, okay? And then the last thing we'll do after that today is piecewise. So we're almost done with today's lesson. Okay, I'm just gonna zoom in on this list right here. You have it on your paper. Sorry, it's so small, but I just want to make sure that you have room to write what you wanted to write. So these say identify which of the 12 basic functions fit the descriptions given. And I'm talking about those 12 BFFs that we had to memorize. So the first one says 4 functions that are odd. Which of the BFFs are odd functions? Remember, odd is the same in the first quadrant and the third quadrant.
It's the natural log. Is that?
I don't think that's odd. Okay, reciprocal is. What else is an odd function? Same in the first and the third. Say again?
Cube.
Cubed is.
Exponential.
Not exponential,
Natural.
not natural. Not logistic,
Square root.
not square root. Linear is. Remember, these are all the same in the first and the third quadrant, so linear is just a straight line, and so it's the same in the first and the third. Cubic is like kind of snakes through, so it's the same in the first and the third. Reciprocal has just kind of those little C's that match in each one. The last one's a funny one, the last one is sine. So the way sine works, and it's really only if you look at kind of the first little part of sine, it will continue on with its waves. But when we get into more with sine, I want us to think of sine as an odd function. So sine is my last odd function.
So sine starts at
0, 0. Sine and cosine do like the wave, so. Sine, I want you to know that sine goes through 0, 0, and then just waves up and down from there. Chapter 4 and 5 is all about sine and cosine and tangent, and so you'll know more about sine than you probably ever wish that you knew by that point. But what I want us to think about is if we just took this little part of sine, that is an odd function. So I am gonna argue that sine is odd.
what about the rest of
We just ignore that for what I want you to remember later on. But it is an odd function. Okay, what about 6 functions that are increasing their entire domain? Which 6 functions increase the whole time?
Exponential.
Exponential does, linear does. What else increases the whole time?
Cubic.
Cubic,
Squared.
not squared. Cause I'd argue squared decreases and then it increases. Sine increases and decreases because it waves.
the natural?
Natural log works. LNX,
Square root.
square root works. And there's one more. One of the funny ones.
Greatest.
Oh, I guess greatest integer does. I didn't count that one before. I also counted logistic. What did I guess on this list I forgot cubic, but cubic definitely does. I think logistic also does. Okay, name 3 functions that are decreasing on the interval negative infinity to 0. What is decreasing on the left side of the, what'd you say? Absolute value? Which one? I don't think cubic. Cubic's increasing. Quadratic, the squaring one does. What else is decreasing? On the left side of the y-axis. Not cubing. Reciprocal, there we go. Reciprocal. Okay, which 3 functions have infinitely many local extrema? How many have a lot of peaks and valleys? Sine, sine and cosine, good. And then the last one is kind of a weird one. I would argue greatest integer also has a lot of highs and lows. If you look back at the graph that we drew, like this point is higher than the one before it, so that kind of counts as a high-low point. Okay. Now we're looking for three functions with no zeros. Which three function have no zeros? Reciprocal doesn't have any zeros. What else has no zeros?
Exponential.
Exponential. And I think logistic is the last one. Logistic. All of those have horizontal asymptotes at 0, 0. So that's another, or at the, I guess on the line y equals 0. So you might even mention that they all have horizontal asymptotes. That's why none of them have zeros, because they don't ever cross that axis. All right, there are three functions with the range all real numbers. Oh yeah, G2. Yeah. Which three functions have, what did you say? Linear, yep.
Identity.
Cubic. Linear and identity are the same. What else has a range of all real numbers?
Squared.
That's where. So it has positive and negative y's.
Reciprocal.
Not reciprocal because you have that asymptote. Natural log, there we go. Exponential and natural log are kind of funny. Did I talk to you about those two functions yet? Did I talk about exponential and log? Not necessarily, okay. Let me just, this is one of those things that sometimes I don't know what you've learned. And then I'm gonna talk about it more later, so I'm always like, do I mention it now or do I just like not worry about it until we get to it? So chapter 3 is all exponential and logarithm. So my exponential function, it has that horizontal asymptote and it goes through the point 0, 1. I always think about exponential and logarithmic as like friends. They like always go together places. And they're always related to each other because they are inverse functions of each other. My y equals ln of x is reflected over this origin axis. So like if this was like all one function, this is symmetric about the origin. They are exact reciprocals or flips, I guess, of each other. This goes through the point 1, 0. I don't like need you guys to know those points, but we know that log has a vertical asymptote, right? Natural log has a vertical asymptote and exponential has a horizontal asymptote. Once we get into chapter 3, we're going to be switching between log and exponential form over and over and over in order to solve for x because they are inverses of each other. So I like to think of them together, or when I think of one, I think of the other because they do have a lot of common similarities. So like exponential, its range doesn't have any negative numbers, but its domain is all real numbers. And then vice versa with my natural log, its domain is just positive, but its range goes from negative infinity to positive infinity. So that is one of my ones that has a range that goes to all real numbers. Okay. What about 4 functions that do not have the end behavior? This is in limit notation, but it generally says as x approaches positive infinity, then my function or then my y approaches positive infinity. So we want 4 that do not have that end behavior. So what are 4 graphs that don't end going high?
Natural log.
Natural log does end going up. It's not going up a little slower. What'd you say? No, that one ends going high. Reciprocal, yeah, because reciprocal ends going towards 0. We're ending, not ending up. What else doesn't end up? Identity does end up. It does end. Let me see. Do I have this on here? So I'm thinking about like what doesn't end with like an arrow going up that way. So this one ends with an arrow going up. This one ends with an arrow going up. This one ends with an arrow going up. We just talked about the reciprocal, because if arrow is going towards 0, so it's not going up.
It's cosine.
Square root's not going up as fast, but it's still going up. What did you say, Chase?
Cosine.
Cosine, that's one of them. Remember, cosine and sine keep waving back and forth, so they're never gonna have an arrow just shooting up to the top. They're gonna keep waving in between -1 and +1 forever. So I'm gonna count sine and cosine as 2 of those. Reciprocal, sine, and cosine, and I can think of one more. Logistic. I know that I drew my logistic really big, but remember logistic has bounds at 0 and 1, it has horizontal asymptotes there. So it's gonna get closer and closer to 1, but it's not gonna go to positive infinity. It's still gonna always stay close and close to 1, so we're gonna say logistic is my last one like that. Okay, we've got a couple more on the backside. Is this helping us kind of think about our BFFs a little bit? Like, I'm never gonna ask you a question like this, but if I ask you about odd or even, it's nice to kind of know, well, there's only 4 that are odd. Or if I ask you about zeros, it's nice to know that 3 of them don't have zeros and everything else should have a 0. All right, the last 3. Number 26 says 3 functions with end behavior as x approaches negative infinity, y approaches negative infinity. So we want 3 that do that. So which 3 like are starting low? That one goes towards 0. Which 3 like have arrows, lines, etc. going in that general direction? Linear. What else? Cubic. What'd you say?
I said log.
I don't think log counts because log stays like x never approaches negative infinity. See how it stops here? So since x doesn't approach negative infinity, I would say no. There is just no end behavior that way. I can think of one more. Not natural. One more. It is the integer one. Good job, Monica. My greatest integer one. 27 actually is the same thing as being odd. So this might be a good way for you to think about odd graphs. It said 4 functions whose graphs look the same when turned upside down and flipped about the y-axis. Okay, let's do this with a reciprocal graph. So if I was looking at a reciprocal graph, we know my reciprocal graph is odd. We've talked about that a couple times. This is what it looks like. If I were to, what does it say? Flip it, turned upside down. So if it's turned upside down, then it's flipped this way. And then it's flipped about the y-axis. So then I flip it over here. This would flip into the black one that's already there. And this one would flip into this black one that's already there. So that is one way to think about being odd, is that you flip it across, flip it upside down, and then you flip it across the y-axis and it should be the same. So the ones that are odd, we've already listed, that was number 19, but that's reciprocal, linear, cubic, and sine. So those all count as odds. And so you can go back to number 19 if you want to see more of those. Okay, and then the last one says 2 functions whose graphs are identical except for a horizontal shift. Which 2 graphs are identical? Which ones? Sine and cosine. Very good. And this is something we're going to get into more later. So if I were to do a sketch, sine, those go through 0, 0. So it looks something like that. Cosine goes through 1, 0. And it looks something like this. I did that a little wrong. That's so weird. sorry, it looks funny, but if I were to shift it over, if I were to just even take this part of the line and shift it over, it should be the exact same thing as my sign. And again, I'm just trying to sketch it so it doesn't exactly look the exact same, but that is something we're gonna talk more and more about in the next couple chapters. But sine and cosine are identical graphs, except they're shifted horizontally. Okay, how are we doing? I just hope that kind of helps us organize our BFF thoughts. Okay, we're gonna jump to the last problem on this. We're gonna jump to number 4. We're gonna do our piecewise, and then we can talk about the quiz, and then you can work on your homework. Okay, have you guys done piecewise? Does that sound like something familiar to you? Piecewise function? Yeah, you did it last year. Okay, cool. We've got some pretty basic piecewise right here. And we'll do some more practice in the next couple days, but these say sketch and list any discontinuity. So I'm gonna write piecewise at the top, just so I remember that they are piecewise functions. We call them piecewise because essentially we take one piece of one and one piece of the other, and then we throw them together. We're gonna go through this slowly. You probably have learned this a couple different ways. Every teacher likes to do it a little bit differently. I kind of just like to see what I know and just throw it on the graph. Some teachers like to do little T tables to organize their points, and I'll kind of show you both. Okay, so the first thing to do is notice where is there a change happening at our graph. So we are changing at 0. We have a point that's going to be less than or equal to 0, and then we've got points that are going to be greater than 0. So 0 is my line where things are happening. So I like to mark that, whether it's a dashed line on my paper with my pencil, or with a highlighter, or just knowing that 0, there should be a change. Okay. The first graph is going to be x, which is just my linear function, right? What do we know about that graph? Say it one more time. Good, we're gonna graph it where it's less than or equal to 0, bless you. Are there any special points about the x that we know about? Or does it go through? 0, 0, it goes through the origin. So we're gonna have a point at the origin. And then we know it's a line. And so generally our line would be drawn something like this, right? The only problem is I don't want it on that right side of the graph. So if you like this, you can draw that whole line off and then just erase the parts that we don't want. Now, if that's stressful for you and you don't want to do that, then don't draw the whole line, only draw the part that's on this half of the graph. You also could do points. We could say, okay, we're doing our x, y points, and we know that it's going to be where it's x is less than or equal to 0. We can do 1, -1, -2. And if I plug x in for x, okay, then that point's going to be negative. That's going to be 0. -1 in for x is going to give us -1 out, and then -2 in for x is -2. And that's what these points are right here. Okay, the second one we're going to graph is my squaring function, my quadratic, my parabola. That generally goes through what point? The origin as well. We can draw an open circle here because we're less than 0. However, it is already filled in, so it's going to be a whole circle anyway. And then you can do a couple things. You can just do half of your parabola because you know it's just going to be on that half. You could draw a whole parabola, but then you need to remember to erase the part that we don't want. Or you can plug it in for points. You can plug in, okay, what am I going to be at 0? What am I going to be at 1? What am I going to be at 2? Again, I want numbers that are greater than 0. So I'm plugging those in. 0 squared is 0. 1 squared is 1. 2 squared is 4. So that's how I know these points are part of my parabola. I'll pretend like that went over it. Okay, that's all we're looking at. Did you guys last year have to do a table like this? Is that familiar? Do you want me to keep doing the table? Yes, no, maybe? Sure, okay, I'll keep doing a table. You don't want a table? I'm not looking for a table, but if that's helpful for you, I will keep doing it. Okay, let's look at the next one. Same idea. Graph our coordinate. Again, 0 is where things are happening here. So I'm going to make some kind of note to myself that 0 is where things are going to shift. And my first graph is 1 over x. So that means I'm doing my reciprocal graph on the x that's less than zero. I'm doing it over here in that left quadrant, in that left-hand side of my graph. Again, we can make a chart. And I only like plugging in a few points just so we know. I know it's gonna be less than zero, so I'm not even gonna put zero in. I can put -1, -2, -3. And that's just gonna be -1, -1/2, -1/3. We also, though, I made you memorize the BFFs, right? So you know what a reciprocal function should look like. You can just draw your little C curve down here in that third quadrant, and that is good enough information to me. You cannot draw the C curve in the first quadrant unless you're gonna erase it, because we only want what's on the left side. Okay. Then we're gonna do x squared for where we're greater than or equal to 0. So now I can plug in 0 and 1 and 2 and see what happens when I square root it. Bless you. 0 square rooted is just 0. 1 square rooted is just 1. And 2 square rooted is √2, which is not a very helpful number. So if you wanted to use a more helpful number, we could use 4, and we know that's going to be 2. Or you can know that it's a square root function, and then we memorize what that was, and it goes through 0, 0, and it just kind of shoot out from there. Shoot out from there. So I don't even need super exact points on these, especially because they don't cross each other. There seems to be no like real issue with how they relate to each other, so I didn't know what the BFF is. Okay, last one. This time we've got 3 things happening. So let's graph our coordinate. And this time we want lines at 0 and at 1, because things are happening at 0 and things are happening at 1. Now, this is one example where it might be helpful to do your little graph, your little T-chart. Okay, so this first one right here, I know that I'm doing that at 0 and then everything less to it. So I'm gonna put those numbers into my equation. We're gonna do 0, we'll do -1, we'll do -2. -3 minus 0 is still -3. -3 minus -1 becomes plus, so that becomes -2. And then -3 minus -2 becomes -3 plus 2, which is -1. If it's helpful for you to do that T-table, then I'm gonna go graph those points on my chart, on my picture. 0, -3, -1, -2, -2, -1. And we're gonna draw a line like this. If you don't like that T-table, totally fine. We see that our function is -3 minus x. We know x is a line, correct? We know that negative means that that line is gonna flip. And then we know -3 means that I'm gonna start down 3 units. So I'm, instead of starting at 0, 0, I'm starting down at -3. And instead of having a graph that goes up as I go across the page, my line goes up as I go across the page, it's gonna go backwards. It's gonna go down as I go across the page to get to -3. So again, you can use your transformations to reason your way through that. The next one just says 1. Is there any variable in there? No, so if I were, that's what it is between 0 and 1. So if I plugged 0 into that, what would I get? 1, because there's nowhere to plug 0. What if I plugged 1 into it? What would I get? What if I plugged 100 into it? If I could do this all day, right? So it's just the horizontal line at 1. So at 0 and at 1, it's just 1. However, because it's less than 0 and less than 1, I'm gonna have just open circles, not closed circles there. Okay. And then last but not least is my x squared. And I actually believe it's helpful to do it with a T-table here. If you see squared, you know it's a parabola. And a lot of us just start the parabola down here. But does the parabola go through 0, 1, 0? No, it goes through 0, 0. So in order to know where I'm at past 1, it might be nice to plug in 1 and 2 to see where we go. 1 squared is 1. So the first point that I'm going to do for my x squared graph is actually going to be at the point 1, 1. I'm going to close the circle that I originally had open, because now I do get to include it. When I do 2 squared, I get 4. So I'm going to jump up to 4 so that I make my parabola look like that. Again, you could just know it's a parabola and you could graph a normal parabola and just erase the parts that aren't needed. But it's important to me that we have this point right here at 1, 1, and we know that because of what a BFF graph is and because I plugged that in. So if plugging points in is helpful, do it. Questions, comments, concerns? Okay, that's it for 1-3. Our piecewise is gonna be on your quiz tomorrow. No, okay, let me show you what is gonna be on your quiz tomorrow. If you wanna get your homework out, you can start on that, but let me pull up what your quiz will look like tomorrow.